In this lesson, I'd like to review the equations that govern the behavior of bars loaded with axial forces. So what I want to consider is a bar where maybe we apply some forces, maybe restrain it on one side, and maybe also apply some forces B of x that are force per unit length. Okay, so this is the basic system. The bar is going to be elastic. So we'll keep everything relatively simple. And so there are a set of four basic equations. There's the equilibrium equation. And so the equilibrium equation tells us that the rate of change of the internal force R with respect to position plus the applied distributed load is equal to 0. So that's the first main equation. So that's the equilibrium equation. And so x is just simply the coordinate from the end of the bar. Okay. Clean that up a little bit. So R of x, so for instance, is simply if you have a bar and I make a section cut, and now I'm looking at the bar here, and then interior to the bar is R of x acting here, and then on the other side of the section cut I have the exact same equal and opposite force R of x. Okay, so that's the main equilibrium equation. The main kinematic equation comes from the plane sections remain plane assumption, and that ends up telling us that the strain epsilon is equal to du dx. And so u is displacement, and epsilon is strain. Okay, so I guess I might as well put it up over here. R is internal force. Okay, so these are the equilibrium equations and the kinematic equations, and these hold true no matter what type of deformation you have. It doesn't have to be elastic at this stage. So let's go ahead and now talk about connecting these two relationships to each other. So the internal force can be defined in terms of the stresses, and that says that R is equal to the integral over the cross-sectional area of the stresses. Okay, and this also holds true no matter what. It doesn't matter if you have an elastic or inelastic case. And then the last equation that we need to close the system is the material law. This is sometimes also known as the constitutive relationship. And since we're doing linear elasticity, it's simply that the stress is equal to the Young's modulus times the strain. So the four boxed equations here are the four main equations that govern the behavior of the deformation of axially loaded bars. So we have these two here, and then on the prior slide we have these two. So the equilibrium equation, the kinematic relation, or the strain displacement relation, and then the internal force definition, so its connection to the stresses on the cross section, and then the material law. Taken together, these four equations give me four equations in four variables. So those are u of x, r of x, epsilon of x, and sigma of x. If you want, you can combine them all together, and you can write them as a single equation, d by dx ae du dx plus b equals 0. And in this representation, we have one equation and one unknown. And that unknown is the displacement. So this is equilibrium. In terms of displacement. It's a second order ODE. And if AE is a constant, in other words, not a function of x, it's a second order ODE with constant coefficient. So it's relatively straightforward to solve. And to solve it, you also need two boundary conditions, which you get from either end of the rod in practice.